Live in Ketchikan is the only show of its kind dedicated to our town. This is the television show that spotlights all that happens in and around Ketchikan. Live in Ketchikan is your resource for all good things local. Hey, welcome to another Live in Ketchikan. You may have driven down Tongass and seeing this monster thing built over the course of the past year. But what I'll bet you didn't know is that this thing, Bethe Substation, is a very important part of our community moving forward, and it came in $1.5 million under budget. So power has been all of the talk lately. Let's go inside and figure out what it's all about.
So let me give you a little overview here of how this thing interfaces with the system. So there's two feeders that come out of the Bethe substation. One comes out to Bethe Jackson, which is basically a 12.5 kVA line that goes up this way, and the other goes underground across the highway to that pole there, and that's the Tongass feeder. So the Tongass feeder feeds everything from the airport to the hospital. The Jackson feeder picks up pretty much the 4 schools up the hill and some residential area. So those are the two feeders. And they happen to be almost identically sized. So on a typical winter day, they've got about 3 megs of load on each of them. The 34.5, which is the incoming into the station, is on this line here. And that goes then underground, well, I'll take that back, goes underground right over here and into the station.
So we're at the corner of 3rd and Tongass right now.
3rd and Tongass. So that pole is a 34.5, which is the backbone throughout the whole island. That goes underground, comes into the station, and goes up into the back. And that's the feed point that feeds this train of devices that comes into this power control building, and then ultimately the output goes up Tongass and Jackson.
Wow. So what does this mean for the community moving forward? Because it's big. It's a lot bigger than what was here before.
It is a lot bigger. So before it was a 5 megawatt substation, and we were routinely in the winter months exceeding the 5 megawatts. So we were due to supersize this. This is really supersized. So this is a 12/16/20 megawatt station. And in those slashes, there's additional cooling that comes on that gives you the next level. So ultimately, it's good for 20 megawatts, so 4 times the size of the original substation. In addition, when we ordered this power control building with breakers in for these 2 feeders, we ordered 2 more, identical. And our hope there is in the future we can tap those. Of course, we'll need more wires up in the air, but in future we can do that. We could exit out this
So
plant.
you could feasibly grow with the community.
We could grow for many, many years.
So how many years?
Well, it's hard for me to speculate how fast this community is going to grow, especially this area, but probably a good 20 years.
Wow. How much did this cost?
It cost exactly $3.5 million.
But
We were funded for $5 million through a grant.
Okay.
And we did preliminary.
So you're under budget. Awesome.
Under budget, yeah. We did a tremendous amount of forecasting. We thought it was going to be a $5 million budget, but through excellent purchasing and controls, competitive purchasing, we were able to keep everything below our forecast, and ultimately $1.5 million under budget.
Okay, so here's my question. I live right up the street, so just because this new shiny substation is here doesn't mean that I should run home and turn on all my lights and not worry about anything.
No, we have to conserve power. You know, the problem we have in the winter months, and this is one of those years, one of those water years. Let me go back. Last year we didn't have a problem in the world. Okay, it rained from July into January. All the lakes were spilling through the fall. We had almost full pools going into December. A lot of rain in December, so no problem whatsoever. We did have a small capacity issue come January. We had some single-digit temperatures, but aside from that, water-wise, not an issue. This year, altogether different. We came off that superb water year, a lot of runoff off the mountains, into the driest October on record.
True.
Okay, so that dry October followed by a mediocre November put us in a hurt. So in terms of monitoring our lake levels, we have something called a guide curve or
And
rule
I
curve.
go on the website a lot
You
because
do,
there's
okay.
the red, yellow, green light on the website where you can look at the lake levels. I like that.
So we're a little bit behind these rule curves. So when you're behind a rule curve, going into December, you know that a diesel burn is imminent. So let's talk about that a second. So starting in October, at the very end, you know, we had a little cooler than normal temperatures. It was a little drier, a little cooler. Loads were a little bit higher. They have been this way now since that time period. And right now, they're a little bit higher than they ever were this time of the year. Of course, you have the Christmas loads too, right? The days are shorter, so the lights stay on longer. So all of this combined, we're drafting the lakes very, very fast. Swan Lake, our biggest reservoir that we have access through SEPA, was drafting at over half a foot a day at the beginning of the month.
Drafting meaning going down.
Going down, sucking
Okay.
it down. It got to a point where we were drafting it nearly a foot a day.
Wow.
And we had about 28 feet before we get to a particular line where we have to take mitigating action. And so when you look at that across the calendar, it didn't look good. Colder than normal temperatures, slightly colder, slightly cooler. But that means the precipitation that comes down is in the form of ice and snow.
Yes, like today.
Like today. So you don't see that in terms of inflows into the reservoir. So in gross numbers, we have about maybe 50 days, maybe a little bit less of water in the reservoirs before we hit a point where we're mandatory have to run diesel. So when you look at those 50 days, where does that put us? That puts us into February. February, we're going to be, oh my gosh, what are we going to do? So we decided to do a little preemptive diesel burn. So we're burning during the peak periods in the morning. We're trying to keep a second unit from coming on at Swan Lake, and we're trying to extend that reservoir level as far as we can until we get some maybe rain on snow event to extend that. Once we can get that comfortably into like the April time frame, and we can start seeing that we have inflows that'll supplement that, then we'll be home free.
Okay, so talk to me as a homeowner, the person sitting in their house. How many people, say, how many households, what could they do, and how many households to, say, give us an extra day? Trick question. Like if each household turned one light off, or if each household turned a TV off, or something along those lines.
That's a great question. You know, I like that question. That's going to give me a chance to really comment, I think, where the pressure point is. And I know you and I have had some of this conversation before. The pressure point really here in Ketchikan is space heat.
Right.
It's electric space heat. Not so much the lights, although the lights are going to save, so any kind of saving. Lights, certain appliances, you can get energy efficient appliances, all that's great. That's all a step in the right direction. But the critical component that we see winter months is space heat. So I watched an event here in Ketchikan, I think we call it Black Friday. And I know from my friends in the north in Petersburg, they said about 1 megawatt of space heating units walked out in the parking lots in their events.
How many space heating units is that roughly, would you say?
I don't
Hundreds,
know what the
right?
Hundreds. And here I'm going to say 2 to 3 times that amount, right? So
Wow.
all the stores, all the big stores here were selling them, and they went out. And so when it gets cold like this, especially in the morning or in the evenings, that's when those are being plugged in and being turned on. So space heat is the number one felon. If we can reduce that by a couple of megawatts, that would be ideal.
Okay,
Now, how
so
do we do
let's
that?
say 2 space heaters per home. And I'm going to use my house as an example. 2 upstairs bedrooms, right, that aren't well heated. And 2 space heaters. If you could climb in your bed at night when it's chilly, turn off those space heaters and add some more blankets.
Or at least turn them down. Now
Yep.
the other thing too is I hate to tell people, you're gonna shiver through the night. That's not the right answer either. But if you have some other alternative fuel, say you have a wood stove, fireplace, even if you do have fuel oil, so it'd be a small sacrifice in fuel oil. And right now, actually, fuel oil and the conversion and electricity are very, very close. So it's not a tremendous loss. But if you can convert, that'll save energy for everybody else. So a little contrast on what was here prior to this, and then of course the changes that we made. So this area was totally different, and it went uphill pretty fast. So when we started excavating after we got all the pieces out, and I'll talk about those, we actually came down 23 feet, so you can see the block wall in the back. We came down 23 feet to get this a little more level with Jackson Street over here. So that gives us a much better access to the components, etc. And we also opened up the size of the site. So when
and it's quieter too.
Oh, Jesus, it's much quieter. I'm going to comment on that. But we had to acquire a little sliver of property here from AT&T, and that took us 8 months to negotiate.
Really?
So it turns out that sometime in the 50s, 60s, maybe 70s, the original site encroached upon that property, and nobody ever knew until we wanted to do this and did surveys. When we did the surveys, we thought, oh gosh, there's a little sliver here that is not even ours. So we went and made all that right, and then opened up the site for what we want to stick in, because all the components are bigger now, right? The station's roughly 4 times the size. Let's talk about the transformer. The old transformer, relatively noisy. You could hear the hum. Now that hum's got a name. It's called magnetostriction.
Really?
That's the name of the hum that you hear from ballasts and stuff, fluorescent lights.
Okay.
When you hear that 60 hertz hum from things that are operating electrically, that's called magnetostriction. I won't get into the
new vocabulary for you.
So transformers exhibit that. The old one was pretty noisy. The neighbors, especially the closest one here, complain about that. So we put extra premiums in the transformer. There's a specification for low noise. And then on top of that, additional premiums to bring it down even lower. So we bought the quietest transformer we could. When I went for the testing, it was built in Pocatello, Idaho. Very proud of that fact, manufactured in the USA. And they energized it to 110% of its load and asked me if I could hear it. And I said, I can't hear it. I can't believe that. So when I told the neighbors that was going to happen, they wouldn't believe me. Well, it's excited now, and now they tell me they can't hear it. In fact, now the complaint is they get too much road noise. So it's fantastic. We achieve what we want to achieve. It's a quiet station.
Where'd the old station go?
We took the old transformer, which was the most valued piece, and we put that in storage in our Point Higgins substation, and we hope to reuse that in another
Oh, very cool.
in another substation expansion, perhaps Ward Cove.
All right, nice.
The regulators, these other cans that you see here, these are like little mini transformers per phase. So there's 32 taps. In the top is a little, like a player piano, and it indexes those taps so that we get exactly 12.47 kilovolts out regardless of the load. So as the load per phase changes, as people turn on their lights, off their lights, on their heat, off their heat, that player piano keeps changing the taps to get exactly 12.47 regardless of the load.
Wow.
So those are 3 of those. Now we also have smaller ones from the old substation, and those are being put in storage. And again, we can put in like a whole new train, perhaps in Ward Cove. That was our thoughts.
Okay.
So we're keeping that in storage. What I'd like to do is take you inside and see the power control building.
Okay.
Probably never been in one.
No.
Okay, let's go do that.
Let's go. You don't realize how massive it is until you get right up here.
It is very massive. You don't have an idea either on that wall. The way the wall was built, the way the transformer was mounted, the braces on the wall, it's all done for seismic activity. Now, you know, we had an earthquake here, what, about a month ago? Mm-hmm. And it was, what, 6.7 on the scale, 180 miles from here, right? And this is all set up for something much more violent than that. So this didn't even rock or move or anything.
Wow.
But it's
Cool.
set up for for some major seismic activity with no motion. Let's go inside.
And I see someone's already in there. This is not an area where you want to go in, and it's always locked.
Always locked. So the one thing that we have to consider while we're in an active substation is something called the MAD, minimum approach distance.
Okay.
And that's 10 feet to an energized part. So if you don't know to recognize energized parts, you want to stay close to me and I'll identify them for you. We'll go into the power control building. We'll stay away from the rest of the
How about I just
site.
not touch anything at all?
There you go. Come on in.
Look at that. Holy smokes.
So the tops of all of these are energized. So we want to stay a minimum of 10 feet from all of those parts. So to guarantee that, we won't even go that direction. How's that?
No. No, thank you.
So let's talk just a little bit about grounding. If you notice, all the fence posts are grounded. This whole area has a very extensive ground grid. It's probably the best grounded substation we have in our system. So we went an extra effort to make sure that the ground grid was very extensive, and it goes down, it's below us, maybe 3 or 4 feet. All the devices are very adequately grounded. So that's the makings of a good substation.
And a safe one?
And a safe one. So if I give you a definition of all of this stuff, I think it's too down in the weeds. So we'll pass that up and we're going to take a walk inside the power control building. You notice the rack of batteries here. So typical of substations, all the devices operate on DC, not AC voltage. And it's all 120 or 130 volts DC. And the reason for that is if there's no power at all in a substation, the batteries are here to open and close the devices to bring power in.
Okay.
Meanwhile, over here, these are what the fronts look like of these breakers that deliver power out onto the poles outside. So this one is dedicated to the Jackson feeder that goes up Jackson, powers up
So
all
can
the
I
schools.
ask a question?
Sure.
Is it, you were talking about the numbers that are going up and down?
Yes.
Is that what that's doing?
Well, this is a meter.
Right.
And this meter gives us a bunch of data. This tells us the amps on each one of the legs, each one of the phases. It cycles through, tells us the volts. This is volts to ground. This is volts phase to phase, 12.884. That's the actual load in megavars, 2.75 on that particular feeder. You can see on this side as well. The combination would be the total load on the station.
Okay.
These two are for future use. The way we design this substation, very flexible. These are switches, mechanical switches here, 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 here. We can switch in one of these breakers into that position.
Why would you do that?
For maintenance.
Okay.
Switch this one in, switch that one off, pull that one out for maintenance, and I can supply Jackson now out of this position or that position.
Oh,
Likewise, okay. I can substitute any of these for the Tongass feeder. So I've allowed myself some flexibility for maintenance.
People like myself, and 99.99% of the people around town, when they think about electricity, they think about going and turning the switch on in their house, or plugging something into the wall, or something along those lines. This is really complicated.
It is.
Really complicated. Huh.
So let's talk about another little complication. All of this stuff needs to get to a central control room so that we know what we're doing any particular instant. We can switch them on, switch them off, read this kind of stuff. And that's all done through a variety of telemetry. So our folks at
As
KPU,
opposed to ESP. No, I'm just teasing.
Our folks at KPU built all this. And we take all the signals, of course, scale down, and we use various devices to scale it down. And then all those signals land on various strips. They go into something called a PLC, Programmable Logic Controller. That gets it put into a digital signal, routed to a routing device, and then out via the telephone lines and into our Bailey station.
Wow.
Within here, we look at about 260 individual parameters associated with this substation. 260 control points through this. Then the box says AMR CCU. What does that mean? That means automatic meter reading. That's the central computer unit. CCU. Okay, so what does this box do? It actually puts a small digital signal on the voltage going out, and that digital signal is picked up by the meter that you have on your house, and it tells it when it's being pulled, and then there's an exchange of information. That meter then puts its data out on the line, and this picks it up. And so the AMR is automatic meter reading.
Interesting.
And this station supplies about 1,600 customers. And the majority of those are on AMR, and so we pick up that information.
Now, what does that mean? Okay, and I don't believe my house may or may not be on this substation. Does that mean that you can literally not have to send the person to read my meter every month?
That's correct.
Oh wow, very cool. Very cool. Is it similar to smart meter technology?
It is.
Okay.
Identical. It is smart meter technology.
Okay. Okay. So feasibly, if I had a question about my bill, you know, most people say, oh no, they'll know when I'm doing my laundry or something like that. But really, if you turn the table, if I had a concern about my bill, I could perhaps make an inquiry, right? If I had a really huge jump in my bill for some odd reason.
Certainly.
You don't want to be calling KPU every day having an inquiry. But let's say there was some oddity in the bill. Then I could call and say, oh my goodness, when you could go in and say, well, you had a big spike for 5 days between these hours. Is that what essentially you're saying?
Yeah, now I like to look at that. You mentioned one of the attributes, and that is you can look back and see where these where maximum usage is.
Right, so I could actually use that as a conservation measure.
You could use it as a conservation measure, but it's also a good troubleshooting tool. So supposing you have electric hot water, and supposing your hot water tank broke, and now you're aimlessly heating hot water and it's on constantly.
And maybe I didn't know it.
And you didn't know that.
Right.
But you could look back into history and see when this event took place. It is a troubleshooting tool. It could be a troubleshooting tool. I know there's also an issue around the whole privacy issue on automatic meter reading. Right now, we only poll the meters once a day. I don't believe that we poll them any more than that once a day. It's done in the middle of the night, and we don't look any deeper than that unless, for instance, a customer actually puts in a request and wants some other detail. Let me tell you about my house. So the house came with electric heat, multiple units and multiple thermostats. When I looked at through the AMR software at my house, another factoid is it's difficult to manage something you can't see.
Right.
So right now, I apologize that we don't have that information available for the average customer to see. You'd have to come down to our headquarters per meter for us. We don't have it available on some wide network yet. But since I had that ability, I could look, and in one day, I cut my usage in by half. Just by looking at the thermostats, programming them down, in some cases turning them off completely, and also I found 2 broken thermostats, one that was on constantly,
Really?
and was able to fix that. So in one swoop, one look, I could make that determination.
Excellent. Okay. Well, I'm very, very familiar with smart meters because, as you know, I moved to Ketchikan from Tallahassee, and I could literally go online on my Tallahassee, which is also a city-owned utility, and go online under my account and see my usage of my meter. And so, and there were times actually when I did that, because as opposed to Ketchikan, the peak demands in the cold months, for us, it was air conditioning.
Certainly.
So when it's hitting 95 and 100% humidity, I was definitely on my TalGov account every day checking my usage. So I don't think it's anything to be scared of. Maybe because I've had experience, I use it as a conservation tool.
Exactly.
I think it's cool.
Thank you. Some of these are common distribution panels. The DC power I told you about, here's a very common distribution panel.
It looks like the one it looks like in your house.
Well, this one here should look identically to the one in your house. This is an AC distribution panel.
Wow.
So it has a main on it, and then all the different loads. So one of these breakers is for lights. Some of the other breakers are for devices on these panels, and then out in the yard as well, we have some lighting out there. So yeah, very, very common, just like you'd have in your house. The difference between AC and DC, basically DC, the polarity doesn't change. So on one wire or pole, it'll be forever one particular charge, and on the opposite, the other. So one will be positive, one will be negative, and they won't change. So typical application would be your car battery.
Okay.
Batteries in a flashlight. If a positive side, negative side, doesn't change. AC now is different. AC alternates, and it's the function of rotating machines, cutting fluxes as they rotate, and they cause polarity to change back and forth. Most of the machines that we use for generating, they have 3 coils in them, or modeled at least with 3 coils. So as the centerpiece rotates and cuts these lines of flux, you get the 3 phases out. A phase A, B, C, and then the AC wavefronts differ from each phase by 120 electrical degrees, so that ultimately at the end is 360 degrees. It's modeled as a phaser as it rotates. That's diving way into the weeds. Apologize for that.
That was a Jacob the Camera Dude question. The reality is that you are $1.5 million under budget.
Through some very careful buying, very
Right.
careful bidding. And we got some very first-class equipment. Everybody loves this power control building. And we specified it to last as long as we could. I won't say forever, but gosh darn, for a long time. So the skin is all marine-grade aluminum.
Wow. Well, good job.
We could have got stainless steel that had been more expensive yet. We thought the marine-grade aluminum would do the same job. A little bit of savings. So it should be impervious to the weather for a long, long time. There's conductors that are also taped for avian protection. And so if a large bird wanted to sit on that, the wings wouldn't span. So the easiest way to get that protected for avian use was to insulate that center phase. It's set up so that a bird can sit on it.
And nothing will happen.
Yeah, nothing will happen. It won't touch the other phase.
No more eagle outages.
Correct.